Hello, this is Sean Bin Long presenting Physics 2211 Lab 2. And to start, the purpose of this experiment was to measure the motion of a real life object under non constant velocity, and then comparing the data from real life's example of non constant velocity to a computer generated model, one with only gravity and one with gravity and drag. This allows people to observe Newton's laws of physics in real life. And a quick result preview is as indicated by the computer model, when both drag and gravity is considered, the predicted model will match the observed model. And some key concepts that we have in this lab is Newton's second law, but this time F net is not constant, and we'll still be using the change in velocity formula, but however, instead of having acceleration, it will be net force divided by mass. And then also, objects in free fall will have a non-constant velocity, which means non-constant net force. Also, when taking drag into account, we're gonna go over a concept called terminal velocity. That's when drag force equals the force of gravity at one point during the free fall, where acceleration will be zero and it will be going down at a constant or at the terminal velocity. And the forces we'll be talking about in this lab is drag and air resistance, or and gravity and weight force. Now here's the computer model of the object's free fall. And here is the tracker model of dropping the paper ball. And the system is the paper ball, the surroundings normal force, gravity, and drag. And some relevant formula and code is the velocity update formula, the position update formula, the force of gravity, Fg equals to negative mass times gravity and J hat, and force of drag, which is negative B, which is the drag coefficient, times velocity squared times J hat. And these are the initial conditions of the paper ball, its initial position, velocity, and its mass. And here's the code for the computer loop with only gravity. While time is less than 0.765 seconds, the only net force that's acting on the object is the weight or the gravitational force, which is its mass times gravity and times J hat. And this one, we're taking consideration of drag and gravity, which has a new equation as time is lower than 0.765 seconds. The net force is W, which is weight, times by Fd, which is force of drag, which is given by the equation negative B times velocity times squared times J hat. And here are some graphs and the similarities and differences. This is the computer graph of only gravity when compared to the tracker model. As you can see, there's some slight deviation, and the y position of it actually goes much lower during this time interval. However, when drag is taken into consideration, which is indicated by the yellow line on the graph, um, the model ends up in a very similar location in terms of y, and it matches the tracker model much more than the model with only gravity. And some possible sources of error that cause the deviation in the graph between the first one, where it's only gravity, is the difference in the center of mass due to human error and drag not being considered. And when we're looking at the computer model with drag considered, the deviation could be explained by the difference in center of mass due to human error as well. And some observations during this lab is that when dealing with objects in free fall, both drag and gravitational force must be considered, and the object will continue to accelerate until it reaches terminal velocity, where force of drag is equal to force of gravity. And some what ifs and what does it means, and would the terminal velocity in this case be the same or different if it was dropped from rest or thrown down? No, the terminal velocity will be the same regardless of starting from rest or thrown down. And what does it mean? Which model predicts the terminal velocity? The model with drag force and gravity predicts the terminal velocity. It happens when drag equals the force of gravity and the object is no longer accelerating. And as indicated by the velocity versus time graph, the slope of velocity changes after reaching terminal velocity. In conclusion, the computer model successfully models the objects in free fall. However, some deviation persists due to human error while estimating the center of mass, and the paper model was successful into demonstrating how an object reaches its terminal velocity during free fall as well.